again so that everybody can connect to the webinar. Hi again, good morning everybody. I'm really delighted to be with you this morning for this very nice webinar that we are actually expecting for some weeks now. We will have the pleasure to discuss about beam shaping with two different technologies, DOE for diffractive optical elements and MPLC for multiplane light conversion. Let me please start with a special thank you to Julien and Clémentine, who are behind the screens, behind the cameras today, and they will be also handling the chat. So if you have any technical issue during the webinar, don't hesitate to ask them whatever you need in the chat, which is on the bottom right of your screen. And we will have a Q&A session also at the end of the webinar. So you may write all your questions in the chat. We will look at them at the very end of the webinar. So my name is Gwen. I'm product line manager at Skylabs, and I will be the one handling today the theoretical explanation. I'm pleased to present this webinar with David.
Thank you, Gwen. So I'm David. I'm a precision engineer at Skylabs for 6 months now, and I'm very, very glad to be here today to make some practical explanation around this comparison between our MPLC and the DOE.
All right. As you have understood, when we have the switch of the camera, we would wait for a few seconds so that we are sure that we are actually online. So what is the agenda today? We will start with some explanation about both technologies, the DOE and the MPLC, and then we will try to go as soon as possible straight to the point, the performance of both technologies. We will have all the time some theoretical explanation, some actually experimental results, and we will support all that by live demonstration done by David. We will discuss the compatibility with industrial setup, the beam shaping quality, the depth of field, the transmission, and last but not least, the robustness to instabilities. We will conclude very shortly with some process results that we have had with MPLC. I will be very short on that because there is a lot to discuss today, but I must start by saying who we are. Skylabs, we are a French company who is actually developing, manufacturing, and selling beam shaping systems. Everything is based on our unique technology, MPLC, for multiplane light conversion. If you want to have, if you have any question about MPLC, don't hesitate to contact us by email later on. But today we will try to go straight to the point, DOE versus MPLC. Let's start by some explanation about how you can make a top hat, because this is today's topic. Actually, there are many ways to do a top hat, and this is very important to start by saying that don't always imagine that this is always made the same way. Here is a simplified explanation. You can imagine that you have some photons which are spread over a Gaussian intensity profile, and you can rearrange them in order to get a top hat. So there are many ways to do that. You could just squeeze them a little bit and you would have a top hat. You could actually take the photons which are in the middle and spread them all around. You would have a top hat as well. You could take the photons which are on the left and spread them on the right, and you would have a top hat as well. At last, even if all the photons are rearranged similarly in two different configurations, they could be going in different directions, still you would get a top hat. All this, of course, is very simplified, but the message is, in all the case, you will see the same thing, whereas this is definitely not the same things. So if you want to do a top hat, there are actually many ways to do that, using a lot of different laws of optics. You could be using ray tracing. That's what you would do when you are using some classical beam shapers, and you use just the laws, the Fresnel laws. You could be using DOE, diffractive optical elements, and in that case, you use the law of diffraction. At last, another way to do that is to use MPLC, and in this case, you use another type of law. You are using the mode propagation. You are using each individual mode, but I will get back to that in the next slides. Let's start by what is exactly a DOE. Actually, behind the word of DOE, there are a lot of things which are hidden, or there are a lot of different components which can be actually manufactured and used. So the one generating the top hats are actually based on a thin microstructure, which is on generally a piece of glass. And this microstructure is of the order of the magnitude of the incident wavelengths. And this is actually altering the phase of the light that is propagating through the DOE. And generally, you have 2 pi phase jumps on this DOE. In that case, you alter the face, and in the far field, you will get the required shape, the one you are targeting, in this case, a top hat, by altering the face. So if you don't want to go to the far field, which is actually far, well, most of the time you will use just a lens that you will put just after the DOE, and in the focal plane of the lens, you will get your top hat thanks to a Fourier transformation. Is everything working well? Yes, sound is good. Okay, great. So MPLC, a multiplane light conversion. I will try also to get into some details about that. So the main things I would say to see is that it's multiple plane. So it means that you will have multiple face plates. So you have a succession of different face plates, one after the other, as you can see on the image on the left. And you have free space propagation in between the face plates. This is very important because this free space propagation serves as an optical Fourier transformation. So over time, we realized that it was much more convenient to do it in a multipass cavity. It means that you will have the light which is going back and forward two mirrors, one of them being textured. This system would be much more compact than the one you see on the left. I also want to insist on another point about MPLC, which is extremely important, is that MPLC actually allows to perform unitary spatial transformation. This is kind of a very technical word, but the idea is that you will have a certain number of modes at the input, and at the end, you will have the same number of modes at the output, and they have to be orthogonal. So we can use a lot of different bases, and we will just tune the mode in order to go from one basis to the other basis. This is another way to sync the light propagation. We don't use the same laws. We don't make our simulation the same ways as DOE, for example. We'll have a zoom now on one very specific function that I want to mention today. This is absolutely based on this mode propagation. It is called mode cleaning. It is a specific feature that we have actually developed at Skylabs in order to stabilize the output beam. So at Skylabs, when we see a beam, we see energy in different modes. So when we see this beam which is shifted, we see energy which is in the main mode, the TEM00 mode, and we see also some energies which is in the higher order modes. So what we will do is that the energy which is in the main mode will follow a specific path inside the MPLC, and it will actually give the expected shape. Whereas the energy which is in the shift, in the instability, will be considered as energy in the higher orders, and it will follow another path, and actually at the end it will be blocked. This very unique feature is very good if you want to handle different instabilities such as tilt, shift, defocus, ellipticity, astigmatism, and other. So I hope that everything is working fine. It looks like there are some connection issues, but let's try to continue the webinar. And we will go to the first survey. This is your time to work, and you will have now a question that is asked: what beam shaping technology you have used? So actually, this is you have multiple choice, and you can answer many of them. You have never used any beam shaping. You have used a DOE. You have used a refractive optical elements. You have used SLM, or you have used an MPLC, or many of them actually. And we will give you some time to answer. It's very good so that at the end we can orientate our discussion based on your answers. So it looks like actually many of you have already used DOEs and SLMs. So I guess that we will close actually the survey and show you the different results. Great, thank you very much, Clémentine. So it seems that some of you have already used an MPLC, and many of you have already used DOE. It's logical because it is actually spread all over the world for decades now. And it is good that you have already used a DOE, because now you will see that what we will show is what you have seen when you were using the DOE. And now you can see also what you could get when you are using an MPLC. So let's get back to the presentation. And now we are starting the most exciting part of the webinar, the performance demonstration. So we will start with the compatibility with an industrial setup. What does it mean first, being compatible with an industrial setup? It means many things for us at Skylabs. It means being compatible with the scanner and the f-theta. In that case, you want to preserve the shape over the whole field of view of an f-theta, and you want not to crop when you are going through a scanner. You want to be compatible with a USP scanner, femtosecond scanner. That means to preserve the pulse duration, but that also means that you want to handle the laser instabilities, which we will discuss later on. At last, you want to be compatible with the machine, having something which is very compact and which has a small output in order to avoid complex telescope if you want to have a small shapes in your processing plane. So now I will leave the ball to David to present the setup we are using.
Okay, thank you very much, Gwen, for all this explanation. We'll try now to present you the different setup we will use this morning. I will at first present the theoretical setup of the Canon pulse. You can see it on your screen, and we will use a collimated source, of course, with a waist of approximately 1 millimeter diameter. Then we'll use a beam expander in order to have a beam which will be around 500 micrometers at the input of the Canon pulse. And then we'll do the measurement at the output of the module using a data array camera. We can show you this on the setup. I think everything is okay on the camera. You will see. Okay, great. We are on screen, so you can see just over here. Martin, if you can go just over there, you have here the collimated source. Then to go to the first mirror. Then we will have just over there the beam expander, and here we have just two injection mirrors which will help you to inject the light into the Canon pulse module. That's as simple as that. There is nothing else on the setup. Now we'll try to see what is the DOE setup. So we just have a collimated source. Then we'll use the same beam expander in order to have the right size at the input of the DOE. Then you will see the DOE and a lens, as Gwen said during the theoretical explanation. And then we just have a transport telescope with a magnification of 2 in order to have quite the same size in the focal plane in order to make the right comparison. We'll try to show you this setup. You can see just here the collimated source. Then we just have the beam expander. Then the 2 injection mirror. Here we are the DOE and its conjugate lengths. And we have just 2 mirrors over there. And this telescope I speak about just over there.
Thank you very much, David, for presenting today's setup to our audience. So let's start with probably the most important, the beam shaping quality. We are doing beam shaping, so we want that to be of high quality. And we will start by defining some criteria in order to qualify the quality of the shape that both systems are providing. Let's start by shape efficiency. Shape efficiency is actually probably the most relevant criteria that we can have for a top hat, but it's not very useful. So I will try to explain it. The idea is to see what is the real useful energy inside the top hat compared to the total energy that you have outside of the systems. So you will have a threshold that you will put at different levels. And in each case, you will try to see what is the area in which you have the whole energy, which is behind the threshold. So it means that whatever energy is above the threshold, you will not take it into consideration because somehow it's useless. It could have been to the threshold and your process would have worked. And whatever part of the beam where the energy is below the threshold is not taken into consideration as well because the process will not happen, whatever process you are having. So you have this ideal 3D shape, and this is the energy which is inside that you want to consider relatively to the total energy, as you can see on the different images. We will also try to discuss about beam uniformity because this is a very good way to see how homogeneous a top hat is. And it is as well an ISO standard. So most of you have already used it, I'm sure of that. And actually, it is also what you have when you're using most cameras, like a data array camera. So whenever we are doing some measurement with a camera, we can see it directly on the camera. And that's what David will show later on. So what you want to, how you want to understand that criteria, the idea is that you have, you will sample your top-hat intensity profile, and you will try to have them on the graphic, and you will see how the intensity is spread over the different possible intensities, and how far the intensity are spread compared to the average relatively to that average. So the example on the right, I think, is pretty clear. In the first case, everything is at the same intensity, so the spread is very small compared to the average. And at the bottom, it is very well spread compared to the targeted intensity. And in that case, you will have a uniformity which is higher. So we must understand also two things. This is a ratio, so it's in between 0 and 1, and you want it not to be straight, so you want it to be the closest possible to 0. At last, we must discuss about sharpness, even if somehow the sharpness is included in the other criteria as well. This criterion is important because when we want to compare top-hat, we should compare them having the same sharpness, because a lot of things depend on the sharpness. The compatibility with some numerical aperture of your system, or actually the depth of field depends on the sharpness. So we define that as the T over L ratio. T is actually the transition length of the top-hat from the threshold to 15% of the threshold, and L is the length that is defined to get the optimal efficiency of the top-hat. So now that we have defined the different criteria, what do we get with MPLC? So this is the system that we will be actually discussing today. This is our study case. So this is what we call a sharp square top-hat, and we are having a shape efficiency of 58% with a plateau uniformity of 0.13. So this is actually a pretty good shape. As you can see, a very nice square, pretty uniform and pretty efficient. Even if we don't discuss that today, I would like also to show you what we have when we have smoother shapes. Why that? Because we want to say that it's not because it's sharp or it's smooth that it's going to be less or really less good. Of course, the efficiency is a bit lower when it's smoother because you have more energy in the wings of the shape, but still our smooth top-hat are also very efficient, and they have a very nice plateau uniformity of 0.1. And I will also discuss the DOE. So on that point, you have to believe us. This is an industrial DOE that is actually at the state of the art, and we did really our best to align it the best way. And actually, it looks like at the end, to get the better square top-hat, we had to have it turned of 45 degrees. And when we do our analysis, we have to return it in order to make the calculation of the shape efficiency. And as you can see, this is not perfectly a square, but this is the best we could do. The shape efficiency is of 22%, and the plateau uniformity is of 0.42. So let's go now again to David and to the live demonstration.
Oh, okay, thank you, Gwen, for all this explanation. We'll try to show you now right on live what are the shape we obtain with these two setups. We will begin with the DOE I'm actually measuring. The data array is on the place I showed you before on the setup, just over there. We just align all these elements in order to have the best shape on both systems. And you can see just over there that the shape we obtained on the data array camera with the plateau uniformity, which is quite good, and the shape, which is a square. As Gwen said, we have to turn this shape on a 45 degrees in order to have the best plateau uniformity. We'll show you now, if you let me just 1 minute, I will go to the Canon Apples setup. Just put on the camera. Okay, we are on an auto-tune function on the camera, so it just take a few seconds in order not to saturate the detector. Okay, great. Here is the shape we obtain at the output of the Canon Apples. As you can see, we have the shape that Gwen showed you in the presentation. You can see if I just turn my crosshair in order to have something which is more relevant, you can see that we have this plateau uniformity, which is quite good, around 0.1, and we have quite the same dimension of the shape in the focal plane.
All right. right, so switching back to the presentation. Thank you again, David, for illustrating that in live. Depth of field. So we are now reaching something which is more complicated. Depth of field is actually, I'm very sure that most of you know, believes they understand very well the depth of field, but I will try to start by saying that depth of field is actually very complex because it's again a question of criterion. So depth of field for a Gaussian beam that most of you are using most of the time, I guess, is actually pretty straightforward. It is defined by the Rayleigh range of the Gaussian beam, and this is where you have actually 1 over E square of the energy is the waste, and you have actually the radius of the beam, which is square root of 2 of this initial waste. But the depth of field depends on a lot of things, actually. It depends on the beam dimension, it depends on the sharpness, and it depends on the technology to be used. So when you want to go to a top hat, you have to be very careful on comparing the right things. Because it depends on the dimension, we will start by something very easy somehow. How do you define the dimension of a top hat? Actually, it may look very easy, but there are many ways to do that. You could say that the Gaussian beam in red in the screen is the same dimension as the largest curve because they have the same diameter at 1 over E square. But at the end, you see that they are very different beams. So why taking that criteria? Why would that be better than taking the half width maximum? Why not? This is a curve in the middle. This Gaussian beam in red is having the same dimension as the middle curve in the middle if you take half of the maximum energy. Otherwise, why not? You could take the plateau. You could take that they are having the same diameter at 80% of the maximum. And in all the cases, if you take different dimension for the top hat to compare it to the Gaussian, you would get different Rayleigh range. And at the end, you wouldn't really know what you're comparing. But never mind, today we are comparing top hat, so it's okay. I was just saying that in order to say that when you want to compare it to the Gaussian, it is not that simple. So whatever percentage of the Rayleigh range we will take in the next slide, this is to compare top hat in between each other and not to compare it to Gaussian. If you want to compare it to Gaussian, the best would be to compare systems with the same actually sharpness, with the same slot on the edge of the beam. So how will we compare things? So in the DOE and the MPLC top hat, we will define the depth of field in percentage of the Rayleigh range, because still it is a good way to compare the different top hats, and we will measure the dimension at 1 over E square. We will look at visual profile because it's very good to see, do you think that this shape is still a very beautiful square that will be very useful to our process? We will use more precise criteria, the shape efficiency and the plateau uniformity. So let's start with the MPLC. This is a curve saying what is the theoretical efficiency versus the depth of field for 2 different sharpness. This is very important to understand, and I want to say that this is a simulation result. This is theoretical data for a sharp top hat of 0.1 T over L and a smoother top hat with a T over L of 0.3. What you will see is that the sharper the shape is, the lesser the depth of field is. So this is also very important to say, because at the end you have seen that we will compare a sharp MPLC shape with a smoother DOE shape. So we could expect that the depth of field is less with the MPLC because it is sharper. And what you will see is that it is not the case. So let's go now to the depth of field with an MPLC. So we have an output beam of 500 micrometer, which gives an equivalent Rayleigh range of 190 millimeter. We have looked at what you get when you are at the Rayleigh range divided by 10. You can see that you have still a very nice efficiency of 49% and a very good uniformity of 0.12 only. In the case of the Rayleigh range divided by 10, so you're a little bit further from the best focus, you still keep a very nice shape with a very good efficiency, and you have still a very low uniformity. Let's go to the DOE now. So we will start by a screen. So we are using a DOE of 300 micrometers. The equivalent Rayleigh range is 70 millimeter, and we will screen over the depth of field by step of 1 millimeter. What you can see in the image on the right is that very quickly the quality will degrade. You will have more energy at the output of the top hat in one direction, and you will have more energy in the center in the other direction. And you can see on the graph, I know it's written very small, but still I hope you can see it, that we are only scanning for a very few millimeters. So when you are already at 4 millimeters from the bed focus, which is only 0.05 times the Rayleigh range, you have still a shape which is very distorted. So now let's make the analysis of the shape. So when you are at the Rayleigh range divided by 20, you have a shape efficiency of 23% and a plateau uniformity, which is already increasing quite a lot to 0.26. When you are even further at the Rayleigh range divided by 10, the plateau uniformity is increasing quite a lot, reaching 0.38. So we will again switch to
Okay, thank you, Gwen, for all this explanation. We'll try to illustrate this phenomena using our two setup. What you can see on the screen, we are still on the same position that we used on the former experiments. So we are on the best focused on the Canon dapples. I will just try to go approximately 10 millimeters after this best focus, and we'll try to see what will be the shape at this place. All right. Let's go. We just have a few seconds in order not to saturate the detector. And here we are. Here is the shape approximately 10 millimeters after the best focused on the Canon Apple setup. As you can see, we have quite very light distortion on the plateau uniformity, but the shape is still the same. And we just have something which is quite interesting. We'll try to go now on the same setup we used on the DOE. Just let me a few seconds in order to make the camera. Okay. Try to zoom on the shape in order to make you. All right, here is the shape we obtained on the last experiment. And we try to do the same thing. We will try to put on the camera of 10 millimeters after this best focus position. Okay, here we are, 10 millimeters. All right, here we are. As you can see, we have a kind of false hotspot that appearing in the shape, meaning that the plateau uniformity is degrading quite fast. And it seems that the DOE has less DOF, less depth of field than that we can have on the Canon Pulse module.
All right, let me on my camera again and switch back to the presentation. Thank you very much, David, for the live demonstration. This is very good to see the depth of field in the reality because honestly, I have a lot of memories in trade shows where people were not believing me when I was saying that we have a really very nice depth of field while doing beam shaping. This is mainly due to the fact that we control not only the intensity profile, but the phase profile as well. And it means that you are having the nice shape with a plano phase in the best focus, and the shape is actually propagating very well, as you just could see. So let's now discuss about transmission. This is going to be shorter, but this is still very important to discuss about that. Again, let's start by what is transmission. This is not that easy, actually. Of course, this is basically the output energy divided by the input energy, but not only. 2 points must be discussed. First of all, in the DOE, you have a lot of useless energy, which is inside the different higher order modes all around the shape. And this has to be taken out because it is absolutely useless. And in the case of the MPLC, we have also some additional losses, but it is very different. This is due to mode cleaning. So somehow it's not degrading the beam as the higher order are doing. It is actually improving it because we lose energy because we stabilize the beam. Anyway, we still lose energy, that's a fact. So the loss in terms of energy due to mode cleaning, as you understood, actually depends on the beam quality and its stability. So we cannot say in advance how much you will get. It depends on your laser, and it is actually changing a little bit from one laser to the other. So with the MPLC, in our case, we are using a low power source. So you understood it's not a femtosecond laser, and this is actually of a very nice stability because it's fibered, and it's fibered output, I mean, and we are having 92% energy transmission for the systems. I want to say also that we expect to have in between 80 to 90 when you are using an actual real femtosecond laser. It depends on the laser. For the DOE, we were seeing on the datasheet that it was supposed to be 96%. When we did the measurement here, taking out all the energy inside the different lobes, we measured roughly 89%. So we will now go to the live demonstration so that you can see that the transmission as are expected.
Okay, thank you again, Gwen, for all this explanation. For this demonstration, we will use a quite simple power meter, and we will try to measure the power at the input and the output of both of systems. Here we are on the Canunda pulse setup. As you can see, I just put the power meter just over there, and we have the measurement, which is around 2 milliwatts at the input of the Canunda pulse module. And we'll try now to make the sensor at the input of the Canunda, and we will measure the transmission. Here we are. Oh, seems we have quite some issue. Okay, the transmission is a bit low. We'll try to optimize it on a few seconds. Sorry for that. Okay. Okay, we will make them. I will try to set up this transmission by the end of the webinar, and I will get back to this at the end of the webinar, maybe during the Q&A question. We'll try to measure this transmission for the DOE. Okay. Okay, here we are. Can't see the data. Okay, so we are approximately 3 milliwatts, and we try to measure it at the output of the DOE. I think that we do have still a problem. I don't know why. Okay. Okay, it seems we have a little problem on this demonstration. We try to get back to this by the end of the webinar. Sorry for that.
No worry on that. We still have some time. And anyway, I know that we have a few slides of explanation following. So I will carry on the presentation, and we will get back to that later on. This is live demonstration, so it happens. Okay, so now we will, last but not least, reach the robustness to instabilities. This is a very important topic, and this is something where it is important to take some time. So first of all, why do you want to stabilize the output beam? Well, we made some simulations some time ago, and we saw that when you have instabilities, which are typical in the typical range of some femtosecond laser, it is actually extremely difficult for all type of technologies to get a stable output and a nice output. So you'd have kind of a distorted beam. So when we started to manufacture beam shapers for femtosecond lasers, actually at the very beginning, we saw that we have to invent this mode cleaning and to stabilize the beam using mode propagation. Otherwise, we would never get a very nice shape. Not even actually if the beam were stable, and even more knowing that it is not very stable. So as I was saying, this is not easy. We have to take some time to explain things. Again, we want to compare things which are comparable. So if you want to compare instabilities for two different systems, it is not just about comparing microradian and micrometer, because we have to compare things at equivalent diameter and equivalent divergence. Why is that? If your input beam at the laser is having whatever micrometer shift, if you use a beam expander to reduce the beam to enter your systems, this shift will be reduced as well by the same factor. So every time when we discuss the shift or the tilt due to instabilities of the laser, we will talk in percentage of the waste and in percentage of the divergence of the beam where we measure it. This is the most relevant parameter, and this is a good way to compare things which are comparable. Again, we want to have criteria. What does it mean that it is stable if you don't define a criteria, in a criterion? We will go for visual aspect, because this is always very good to see the shape, to see how top hat it looks like. And we will also go for shape efficiency. Is it still efficient? Do you still get your process done? We did say a few minutes ago that this mode cleaning was, of course, having an impact on the transmission of the system. So I want to make a stop on that so that you see that we are not talking about tens of percent of energy loss. We are just talking of a few percent. So here is the transmission that we are having when we are only tilting the beam, when we are only shifting the beam, when we are having the beam waste, which is either too big, either too small, or when we are having defocus. So the waste is of the good size, but it is not at the right position in the systems. What you can see is that for actually pretty big differences, 10% of the tilt, 10% of the shift, 10% of the waste, 10% of the relay range, in every case we have a transmission loss of less than 5%. Actually, most of the time it's only 1 or 2%. It is important to say that you won't lose a lot of energy due to the mode cleaning. So now the robustness to misalignment. We will start with multiplane light conversion, and we will focus on shift. Here you can see that we are having a huge shift, half of the waste. No laser are having half of the waste instability in terms of shift. Of course, what you can see here is that even at such a shift, we are still preserving a very nice shape at the output of the MPLC system. The shape isn't changed. The efficiency is very good. The uniformity stays very low, and we are preserving as well the sharpness of our beam. So now we will be looking at the tilt. So we will again be looking at huge tilt, half of the divergence in one direction or the other. And you see that we do preserve a very nice shape over that very big range. The efficiency stays very high. The uniformity is actually a little bit degraded, but it's still pretty good. And we have a very good sharpness. These results are some results that we have had with one of our partners, Glow Photonics, and it was actually for them, the objective was to have a very stable output in terms of depointing, and they were introducing a depointing up to 160 microradian at the input of the system, and the output was having a depointing of only 10 microradian with hardly no energy drop and no change in the beam shape and the beam size. So that's an example of what you can get with our systems. Let's go now to DOE. So we will start by the shift. When you are shifting the beam, in the experiment that we have done, we try, of course, to decorrelate the shift and the tilt. So we are only shifting the beam on the DOE. What you will see is that it's extremely robust in terms of displacements. You can shift the beam, still the beam stays at the very same position. But you have a huge impact on the shape quality. You can see also on the image on the left that we are moving by step of 0.04 times the waist, and the shape is always is very quickly changing. You have more energy on the right or more energy on the left. You see also that it is impacting a lot the sharpness of the beam. So now let's go to the tilt. So this is when actually we tilt without introducing shift. So this is something very important. The note is important. The pivotal POM is on the DOE, which never happened on the reality. So we are having only tilt, but we'll tilt the beam around the DOE. So in that case, you see that the shape is very well preserved. You always have a pretty nice top hat, but it is moving quite a lot. It is, I would say, just following the expected law. It is following the Fresnel law of the conjugation inside the focal plane of a lens. In the real world, you will have both tilt and shift of the time. This is a must because the pivotal point is actually inside the laser most of the time, or in between the DOE and the laser. So this is actually what it means is that you will have an impact on the shape and in terms of position and in terms of quality. So we will go to the survey number 2, and we will give you some time. Thank you very much, Clémentine, for this survey. And this is a funny one. I want you to be involved in the future of Skylabs, and I want you to choose, do you like this live demonstration? Do you like the comparison in between technologies? So there is a lot more we could do in future. I don't say it's easy because it took us a lot of time to organize, but do you prefer to have webinars based on more on process results? Do you want to see other webinars for technology comparison? So we could say a lot on that. We could compare the MPLC to generate top hat, so similarly to today, but MPLC versus refractive optical elements. Refractive optical elements, we could, for example, I think I will mention it, we could, for example, compare with a pie shaper. We could also focus on mode cleaning. As I said, mode cleaning is very important for us. And even if you don't shape the beam afterward, it is actually very useful to just stabilize it. We have many people, I think, in the audience actually who are interested in only stabilizing the beam. So the highest competitive technology is active solution. And we could compare, the truth is we don't have active solution, but we can buy one anyway. And we could compare the performance of only mode cleaning compared to active solution. It would be again for more microprocessing. We could go to very different topics as well. I would be happy to compare Bessel beams. We have done that in the past. Actually, we have some papers at ICALEO on that. We compare the performance of reflective Axican made by us. It's generating a very nice Bessel beam of a very high quality with a refractive solution, so a more standard Axican, a transmissive Axican, and mainly the impact is actually on the Bessel quality. The most exciting, but definitely the most difficult, would be to look at high power systems. We have some systems which are compatible with high power multi-kilowatt CW lasers. This is made to do, for example, laser beam welding. And we have a system working very well, which is providing a ring. And what would be quite nice would be to have myself here in Skylabs and David going to the Institut Maupertuis, our partner, which I want to say hi to them, and do a live demonstration comparing the performance of a double core fiber laser with our ring shaping technology. It looks like you are very interested in everything, but you don't want to see other webinars. So we will finish the vote. Thank you, Clémentine, for closing that. And it is very nice because we know that we have to do a lot of new webinars. So we are happy, I think, David and I, to do that. Let's get back to the presentation and to the live demonstration. I think David is ready.
Okay, thank you, Gwen, and sorry for this little interruption. We'll try to get back to this transmission measurement. As we said before, we'll try to measure the transmission just after the Canada pulse module. And this time, you can see that you have something around 0.74, which is roughly 0.88, 0.89% transmission. You can do the calculation, and then we'll try to make the transmission as you saw on the DOE. We have something around 3.16 watts at the input of the DOE, and we'll have at the output of the DOE approximately 2.86, that is to say more than 0.9% transmission.
I think you can carry on with instabilities.
Okay. Trials around stabilities of the beam shaping. We'll try at first to tilt the DOE for a few round of the torque. Okay, here we are. We will try to move the DOE laterally speaking using a little knob. We'll do this. Okay, here we are. As you can see that the uniformity is quite changing. We do have some hotspot that is going on the DOE, and you can see that the shape is quite the same, but the uniformity is quite decreasing. We'll try to do the same thing on the Canunda Pulse module. Just a few seconds in order to move the camera. Okay, I think here we are. A few seconds not to saturate the detector. Okay, we do have this. We'll try to make a little translation using the 2 injection mirror. We'll do this like this, and we'll get back to the like that. Okay, here we are. As you can see, we still have the same shape, we still have the same plateau uniformity, meaning that we are very stable from a little shift of the beam. And I get back to Gwen for the end of this presentation.
Thank you very much, David. This is really nice to see all that in live. So time is flying. I'll have to be quick on the last slides, but anyway, it's only 2 more slides, and then we'll be at the Q&A. So be patient. So process results, I will be extremely short on that, but I just want to say that we have multiple shapes which are available, and all those shapes are useful to do multiple different processes, and in every cases, surface texturing, microfluidic chip welding, and drilling, we have proved to be performing very well and improving those different processes. What message should you take home? Well, MPLC is working very well for microprocessing, of course. And when we do develop the systems, I want to insist on the fact that we focus on 3 different very important aspects. The shaping quality, of course, we do beam shaping. So we want the shape to be good. We want it to be diffracted limited. And we want to have a preserved depth of field in order to have your process very robust. Again, we want to focus on the yield improvement by having the optimal shape with a very good efficiency and the pulse duration, which is preserved. We want the process to be robust, the system to be compatible with your setup, and we do stabilize very well the laser beams. Let's conclude on the DOE versus MPLC topic. In similar condition, we have proved that actually MPLC presents a higher depth of field compared to the diffractive optical element. Mode cleaning is key for the MPLC systems, and this is actually the feature that enables to have a very high shape quality, no matter the laser input, and despite its instabilities. So this is it for our presentation, and we will now go to the Q&A session. So, great. We are now in the Q&A mode. Give me a second to publish a different question. What does this element mean? I guess that it has been answered already. It is already answered, as I was saying. Okay, so another one. What are the typical losses when you use this type of beam shaping? So I believe that the question was after the transmission part. So as I did say, at least for MPLC, it depends on the laser. We have actually used now different laser manufacturer in the real world, and the transmission is when you are using this laser between 80 to 90% in the best case. Can this be used for high energy femtosecond laser? What do you mean by high energy? So the standard module actually are made for 100 microjoule, but we have proved actually that we can work to more than that. I hope that we will have a system available at 1 millijoule in the next few weeks or months. So follow us, and in conferences in the future, we will show that very, very soon. And I just want to insist on the fact that even if it's not a standard product yet, it is definitely available as a custom development. Now the question, can the MPLC also used for beam splitting or just for beam shaping? Yes, it can be used for beam splitting. What is the evolution of the shape with increased average power, thermal defocusing, deshaping? This is actually an excellent question, and it is difficult to answer. The main issue, because there is an issue, is not so much about the system. The thing is that most of the time when you increase the average power, the laser beam is changing a lot. So I'm sure that the laser manufacturer will soon in future solve that. But for us, the difficulty is that for very high power laser, like maybe 1 kilowatt laser, for now, generally the output of the laser is changing really a lot. So yes, it can be used. There is not so much of thermal defocusing inside the system, but we are also working on that. Higher power and higher energy is our target, and we are definitely addressing that currently. What is the type of the laser beam? I don't know if the question was for the live demonstration or for the real world. For the real world, this product is made for pulsed application, so femtosecond, picosecond, nanosecond, even if it was mainly used for femtosecond for now. Today, for the type of laser, maybe David can answer?
Yeah, I will get back to Gwen. Yep. The laser we use today for the demonstration are low power laser, continuous, something like a diode laser, which are used with the collimator in order to have something which is quite well collimated. But it's only a standard off-the-shelf laser that you can find on the online supplier or something like that.
Okay, we have a lot of questions. How precise does the Gaussian input beam need to be? How precise? I don't know exactly what it means. How precise? I guess it's you are having in mind the M square. We define our product for M square inferior to 1.3. It doesn't mean that if it's higher than 1.3, it will not work. It's just that the mode cleaning at the end will have to clean maybe too much of energy, and it starts to be not the ideal case, and the transmission would be lower. But I want to insist on the fact that whatever the input beam, we could have some custom system which is fitting your input beam if it's not the standard product that you have seen today with David. Or rather, how forgiving is the system in terms of deformed Gaussian shape as input beam? So I guess I've answered that part as well by saying that we have some standard on that. And I guess we will go to the next question. What is the best steepness you could achieve? I think 0.1. So this is close to the steepest topaz that we have done. The truth is that we didn't really try for now to do steeper than that. So we have two modules, what we call the smooth and the sharp one. And maybe we will try in the future to get even sharper shapes. But do we really have to do that? It's not an easy question, because the thing is that the sharper the beam, the more complex it is to transport through the whole setup. So at the end, if we do something which is even more sharper, and if you want to have very small pattern, you will have to have like huge f theta lengths, which most of the time you don't have. So I guess that actually the 0.1 sharpness is actually very good already. What are the drawbacks of focalizing the top at beam? I'm not so sure to understand that question. So Alberto, if you can to reformulate your question more precisely, it will appear in the Q&A later on, and I will get back to that. For both technology, how often do you need to realign the system with the optical path to conserve identical results? So for the DOE, I cannot answer because we did only some low power measurement at Skylabs. We don't have femtosecond laser. But I guess that what you have seen is that it is very sensitive to tilt and shift, and we definitely did take some data which are relevant, which are what you will get with the real laser. In the case of our module, well, I guess that they are not really realigned. Once they are aligned, they are working well and they are stable over time. Is it possible to use 355 nanometers and 343 nanometers? This is, and I guess it is an Asian question because this is an Asian market which is really keen into UV. No, not for now. We have solutions working for UV, for other shapes, but for femtosecond top edge generation, for now, it is not available for UV because UV is really tough. What I still want to say is that we will be releasing very soon at Photonic West the green version of this module. So it's not only IR, it's green now. It will be UV in future, but not yet. Any data on energy density, lambda plus energy plus duration, frequency, area, lifetime, it can handle. I guess, Eddie, the best would be that we discuss that on the phone because this is a very big question and we can provide some data, of course. And I think this is going to end the Q&A session because it is already 9:55 here in France. So I'll get back to the view. Let me go to. Okay, so we are reaching the end of this webinar. This was really nice to do that with you, David. We were really happy to be with all of you comparing the MPLC and the DOE, and we want to thank you all and say that we remain at your disposal if you have any questions. Thank you very much, David.
Thank you, Gwen. Thank you for all of this theoretical explanation. It was great to make this comparison. I hope that all of you enjoyed this comparison. Don't hesitate to ask questions by email also.
Thank you very much. See you soon.
Thank you very much.
Bye-bye.